Hey, 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 it's Quadratic Functions! Chapter 9, all about quadratic functions. And in Chapter 9, Section 1, what we're going to talk about today is the graphs of quadratic functions. Alright? Focusing around this goal of specifically graphing quadratic functions of the form y equals ax squared and y equals ax squared plus c. A lot of times with quadratic functions, there's also the bx in between, so a number and the variable x, but we're just going to focus on these two today. All right, so we're looking at quadratic functions. I believe this is the St. Louis arch. It makes a U shape, and that's what all quadratic functions are going to graph. We know linear functions graph a straight line, absolute value functions graph a V. Well, and exponential functions kind of go slowly up and then up or down super fast. Quadratic functions, what we're going to talk about today, form that U. So we've got a couple of vocabulary terms. Worth writing down, maybe not everything word for word, but a quadratic function is a function of the form y equals ax squared plus bx plus c. So that's the form, and that's important to know because we're going to be dealing with a lot of those this chapter. But the graph of a quadratic function is a parabola. That's a U-shaped curve that opens up or down. So we're going to be graphing essentially U's. I don't know if that's one of the ones I have here for definitions or not. But the second one we have the standard form of a quadratic function. Um, it's just ax squared plus bx plus c, and a is not going to be equal to 0. The reason I put this in here is because it's in descending order. So if you look at that right there, um, it does have the x squared term first, then the x squared, then the constant term. So that's what the standard form is for quadratic functions. The quadratic parent function that we want to talk about is the one that everything else goes off of. The very basic quadratic function is the y equals x squared. Okay, that's one of the ones we're going to graph today. Oh yeah, there's a parabola of a quadratic function, U-shaped. Parabola. We're also going to be talking about briefly about the axis of symmetry. So it's the line that divides a parabola into two matching halves. So it's called symmetry because on both sides it's going to look the same. The vertex is the highest or lowest point of the parabola. So if we have our parabola, this is the very highest point, that's the vertex. Okay? Same thing if it was a low point. And then minimum or maximum. Basically what we're saying is, depending on how the graph is, the vertex would be a maximum for this one. It would be a high point. If we had an upside down U, or a regular looking U, I guess, that would be a maximum. This one has a minimum vertex point. Okay? A lot of little vocabulary terms. We're going to talk about them with each of our examples here. So, quadratic functions. A quadratic function, there's the definition again. There's a couple examples right there. A couple of notes, though. A quadratic function must have a squared term. Okay? If it doesn't have a squared term like all these do, it's not a quadratic function. And the simplest quadratic function, that's the parent function we talked about, is the y equals x squared. So let's talk about that graph a little bit and identifying vertices. So if you have this U-shaped, we have a positive x squared term. Positive, we think happy. That's why I have a smiley face next to it. That means it's opening up. It's pointing up. But when it's opening up or pointing up, it has a minimum vertex point, because the vertex is on the bottom. Opposite would be if you have a sad face or an upside down U. When you're pointing down, that's when you have a negative in front of the x squared. And you would have a maximum vertex point then. So in other words, to determine if a parabola has a maximum or minimum, the coefficient of the x squared term is negative, then it has a maximum point because the parabola opens downward. There's my sad face. It looks like a upside down parabola. That means it has a negative coefficient. If the coefficient of the x term is positive, the parabola opens upward and has a minimum point. All right, there's my little example with the face there. So a couple examples to look at. It says, what are the coordinates of the vertex of each graph? Are the vertices maximums or minimums? So if we look at this, it's the very highest point. For this first one, our ordered pair would be 0 over, up, 1, 2, 3. And you can see from the graph that is going to be a maximum. Meaning it's opening up downwards, so the number in front of the x squared is actually going to be a negative. Here we have a minimum, it's the bottom of it, so it's a minimum vertex, and the point there, it would be 1, negative 1. So your turn. Why don't you pause it for a second? Whoops, my graph disappeared. It's way down here. What is the vertex of the graph at the right, and is it a maximum or minimum? So pause it right now, and go ahead and answer that question, and then unpause it, and you'll see how your answer stacks up against the correct answer. All right, so the ordered pair for the vertex is -2, -3. And looking at the graph, that's the bottom point. It's the very lowest point, so that would be a minimum for the vertex. All right, let's move on. Let's talk about graphing it, actually. So I've got a lot of different parts here. It may be worthwhile to write down these parts and give these some hints about the parts of the quadratic function. So if you look at A, I have two different things pointing at the A. We have that the A indicates if it opens upward or downward. So we talked about that. If it's a positive, it's going to open upward. If it's a negative, it's going to open downward. And then also A affects the width of the parabola. The smaller the absolute value of the width, meaning like if it's less than 1 or less than -1, or closer to 0, it's going to be a wider parabola. The bigger the A value means the faster it's going to go upwards, so it's going to be narrower. So the A value affects a couple things. The x squared value is what indicates that it is going to be a parabola. The C value here affects the height of the vertex, meaning it's kind of like a y-intercept, but it's going to be where the vertex starts. It's going to help us determine where the vertex starts. But then the B value also affects the position of the axis of symmetry, meaning it's also going to affect the vertex. So if there is a B value, that'll move the axis right or left. And we'll talk about that a little more specifically on how it affects it. So let's graph the function ax squared. All right, we have 1/3 x squared. We're going to make a table of values. That's a t-chart. And find the domain and range. So it's up to you what x values you want to choose. I choose like was chosen in this example, ones that'll work nicely with the example itself. So if you use 0, 0 is always a great one to use. 0, you plug in, you get 0. So we have 0, 0. Plug in 3, and the reason we plug in 3 is when you square 3, it becomes 9, and then 1/3 of 9 that's going to be a whole number. It's going to be 3. So we have 3, 3. 1, 2, 3. Okay, so going by 3s, 3, 3. All right, plug in 6, similar thing. 6 squared is 36. 1/3 of that is 12. So 6, 12. So now it's going up faster. That's what happens with the parabolas. They start to round. They start to go up faster. Now, the easiest way to do this is to deal with positives and then just reflect them across that axis of symmetry. So we know the axis of symmetry for this one is x equals 0 because there is no c value. So we can just reflect it across there, and we have our -3, 3, and -6, 12. All right, and that completes the U. It's just the opposite side. So looking at that, why don't you take a look at the steps, if you'd like to write down the steps. Step 1 would be make a table of values, a t-chart. Pick values 1, 2, 0, 1, 2, 3, or other ones that would work best for what you have. Plot those points Reflect the same points across the axis of symmetry. Draw the parabola. That's a lot of steps in one. Couple of hints here. If there is no b value, your axis of symmetry will be on the y-axis. If there's no c value, it's going to actually start at 0, 0. If there is a c value, you'll move it up or down that many places. So that would be on the y-intercept. So why don't you pause it and try one by yourself. We have very similar but different coefficient here. Now we have y equals negative 3x squared. We didn't talk about the domain and range for the last one, but we'll do it for this one. So graph it. All right, go ahead. All right, so here's what I did. I plugged in 0, 1, 2, and 3 for the x values and found the y values to be 0, negative 3, negative 12, and negative 27. So you can see they get farther and farther apart as you go up. So I just graphed the first three, actually. On my graph, I labeled the x values going up by 1, the y's going by 3's. So I got 0, 0, 3, or 0, 1, negative 3, and 2, negative 12. And then I reflected them across, and that's where the red dots are to make my full U here. It also says, what are the domain and range? So for domain and range, remember, domain has to do with the x values. Range has to do with the y's. So the domain, the x's, are going to be all real numbers. I know that's hard to picture right now because it seems like it's not going to go very far to the right. But really, it does, or to the left. It does ever so slightly keep moving over and over and over. So we could go on forever and it'll keep going slowly, 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 but it'll keep going. The range, however, the y values, we're going to say y is anything less than or equal to 0. Because it doesn't go higher than 0. It goes to anything less than or equal to 0. Okay? It does go to 0, so it could be equal to 0. So that's just how you talk about the domain and range. All right. Last thing, I just wanted to talk about applications. So comparing widths of parabolas. If we look at these examples here, it says use the graphs below. What is the order from widest to narrowest of the graphs of the quadratic functions? So we have them labeled. This is y equals negative 4x squared. Sorry. So there we go. We know it's a negative, so it's going down. Now we have 1/4 x, so it's very much a smaller number, 1/4, but much wider of a graph. And then we just have regular x squared, which means you have a 1 in front of it. That would tell us that it's going to be your parent function, and it's going to be a little bit wider than this, or a little bit narrower than the second one, but wider than the first one. So one of the things we talked about a little bit earlier was looking at that coefficient. The smaller the absolute value, so the smallest absolute value is 1/4 there, the wider it's going to be. The bigger the absolute value, the narrower it's going to be because it's going to go up or down faster. The bigger the number, it goes faster. So looking at this example to try on your own, says what is the order from widest to narrowest of the graphs of the functions f of x equals negative x squared or negative 1x squared, f of x equals 3x squared, and then f of x, and these are, you could all say y, but equals negative 1/3 x squared. So why don't you pause it and just try it. Put them in order from widest to narrowest. Go ahead. All right, so the first one, the widest is going to be the one with the smallest absolute value. Negative 1/3 is the smallest absolute value of all of those, so it's going to be the widest one. Then we have the negative x squared, which would be negative 1x squared, so that's the second widest. And then 3 is the biggest coefficient, the biggest absolute value of the coefficient, so that would be the narrowest. It's kind of opposite of what you would think, but that's how you can tell without even graphing how wide or narrow they are in comparison to others. The other application I have for you is the falling object model. We're going to do a little bit more with this, but there is a formula for falling objects that you can use. It's a big thing that you'd use in physics. It is a quadratic function. If you think about something, think about it, falling objects is a common thing. Things fall. But we're not going to go into detail about this. It is just a function that you can use to apply quadratic functions, though. What I do want to end up with, though, is thinking about 5 real-life. I want you to try to come up with 5 real-life examples of parabolas. Now, remember, parabolas are just those U-shaped, um, well, graphs, but there are real-life things in the world that looks like parabolas. So try to come up with 5. All right. And then why don't you go back and think about that goal? See how you what you learned about graphing quadratic functions that are in the form y equals ax squared or y equals ax squared plus c. All right, and that's it for section 9.1, starting off our chapter on quadratic functions, talking about their graphs. So we'll see you next time for section 2.